Manna.
Just wait. Recording has been started. Okay, so good afternoon. Welcome back to Harish-Chandra lecture series on Lie groups and their presentation. It is my pleasure to introduce today's speaker, Dr. Samir Hazra from GITAM University. Dr. Samir Hazra has done his PhD from Srinagar University under supervision of Professor Ambar Habib, and he was also my colleague as postdoc at HRI Prayagraj. And with this, I request Dr. Samir Hazra to deliver his lecture, and also I request all the participants to mute their microphones. Over to you, Dr. Samir Hazra. You may start your lecture now.
Yeah, so thanks, Mona, for the introduction. So basically, this is the fourth lecture on the same title, an introduction to Lie groups and Lie algebra. We have seen introduction to Lie groups. We have seen several different kinds of Lie groups and some, basic theory about them. We have also seen Lie algebras in the mostly in the last lecture. Okay, so a basic introduction has already been given for the Lie algebras. So here, this is the fourth lecture, and I will again recall the definition of Lie algebra. So Lie algebras are, of course, a vector space. So a vector space and some algebra structure is there. For Lie algebra, it is mostly written to be a bracket. Okay, the third bracket. So this is a bilinear map on the vector space. Basically, this is true for any algebra. So bilinear map, if this satisfies these particular two conditions, then we call V a Lie algebra with respect to that bracket. So these two conditions are xx equal to 0 for any x in V. This is called anti-commutativity, and this is very special, called Jacobi identity. So basically cyclic permutation, and if you sum them up, you will get 0. So such things we have seen already in school mathematics or physics, I think. So if we have R3 and if we take the cross product, so this is the cross product. So then with respect to cross product, the vector space R3 becomes a Lie algebra. So most of the Lie algebras we have seen in the last lectures were on are defined on the reals, because they came up they appear as Lie algebras of the Lie groups, and Lie groups are, of course, real Lie groups. Therefore, the vector spaces were naturally defined over R, and therefore the Lie algebras we have seen over R. But mostly here we will consider Lie algebra over any arbitrary field. And for some parts of the of this lecture, we'll also assume the field to be algebraically closed, and characteristic 0. So anyway, if V is any vector space, if we can define the bracket of any two elements, let's say xy, to be 0. So then this bracket satisfies all of this, and therefore V with this trivially defined bracket, is a Lie algebra called the abelian Lie algebra. Well, so if we start with any associative algebra, so basically is a vector space, and then there is this associative dot. So out of that, we can make one Lie algebra. So out of that associative algebra, we can define this Lie algebra as, so basically define the bracket of AB as AB minus BA. Then with this bracket, the associative algebra becomes a Lie algebra. So this is true for any associative algebra, and therefore it is also true for the matrix Lie algebra, M and F. So basically these are the square matrix of order n. And the bracket can be defined by this commutator. Commutator of A and B is just AB minus BA. So one has to check that this actually, this bracket satisfies the Jacobi identity. AA equal to 0 is obvious from the definition. Well, so if we in particular take the traceless matrices, so basically n-cross-n matrices again, but with trace equal to 0, this also forms a Lie algebra. Okay, so simply because trace of AB minus trace of AB minus BA is always 0. So this is closed under this bracket, and all other properties are as they were. So SLNF. So this is the space of all in-process matrices, so traceless matrices, also Lie algebra. So similarly, GLV, this is again a notation. So GLV stands for the set of all linear operators from V to V. V is a vector space. So then we can use the composition of maps, composition of linear maps to define this bracket. So basically TS is again TS minus ST. In such a way, we can give this GLV a Lie algebra structure. Okay, so this is again a Lie algebra. Well, so if we talk about dimension of Lie algebra, then dimension is nothing but the dimension of V as vector space. So the basically dimension of the underlying vector space is also called the dimension of the Lie algebra. And mostly we'll so basically all of our Lie algebras will be finite dimensional in our two lectures. Well, so one interesting question one can just throw here, right here, is that some interesting matrix Lie algebras we have seen. Sorry. Here, MNFSL. So one can ask whether all the Lie algebras can be viewed as Lie algebras or matrices. So that is answered by this. This is a really high-level theorem on Lie algebras. No basic introduction to Lie algebra. Maybe talks about this. But anyway, there's no harm to know this theorem because this gives a bigger picture. So if we take any finite dimensional Lie algebra over a field of characteristic 0, then that Lie algebra can be viewed as a Lie algebra of square matrices with commutator as bracket. So square matrices of some order with the commutator is bracket. So essentially every finite dimensional Lie algebra over characteristic 0, they turn out to be Lie algebra of some square matrices, okay, with the obvious commutator bracket. Well, subalgebras, ideals, they're defined analogously, like groups and rings. Rings. So if G is a Lie algebra, S is a subspace of G. Then if bracket of SS is inside S, then S is called a subalgebra. So a bracket of SS is defined with the following. So you take any element of S, let's say X, and an element of Y, so Y, and then you take all possible linear combinations. So let's span of elements of the form XY. So that is again a subspace, and if that space is inside S itself, then we call it subalgebra. So in particular, if I and G, their commutator, is inside I, we call I an ideal. Some obvious ideals are here. So if you take the trivial subspace and the subspace itself, the full space, they're obviously ideals. One can just check. Okay.
Samir, you have really the notation for ideal you have written wrong.
Notation for
ideal I. So that will be something like triangle, right? So
here
no.
Lie algebras, I have never seen triangle like groups.
Okay.
Yeah.
But
so in any case, this is the definition. That if this is contained in I, then
that's okay. Notice.
Yeah,
but
so
the thing is, I think I triangle should be there, not normal thing. It is analogous to normal thing, right? Okay. Anyway.
So anyway, this is the subset. This is the definition.
No,
now,
that's okay.
Want to express this fact that I is an ideal in G, then in Lie algebra, I have not seen the group like notation. I don't know if people use this, but from the context, it must be clear that whether I is an ideal or not. Also, for some Lie algebras, there may not be any such any proper ideal. So we are calling them improper. So basically 0 and G, they are obviously ideals for all G. And if there is any other ideals, basically other than these two, then we call it a proper ideal. So a Lie algebra, if it has no proper ideal, non-trivial, no proper non-trivial ideal, then the Lie algebra is called simple. Okay. So examples can be given, like SL2F, it has no proper ideal. So this definition actually does not work for dimension G equal to 1. Okay, so if we take a Lie algebra of dimension 1, then it has no proper ideal, because it cannot have G is itself, because dimension is 1, and if one dimension you go one dimension less, it is trivial. So there is no subspace even. But some books do call them simple Lie algebra, rather trivial simple Lie algebras. So therefore, I did not include this in the definition. But anyway, if dimension is equal to 1, then we do not regard this as a simple Lie algebra. Okay. So one example can be given by this SL2F. So basically 2 cross 2 matrices over this field. When characteristic of F is not equal to 2, this is simple. If characteristic F equal to 2, this will be very kind of trivial, which are called nilpotent. And in general, not SL2, if you take SLNF, they are also simple, but a proof is not direct for this fact. So there are many more simple Lie algebras. So given a Lie algebra G, we want to talk about center of Lie algebra. So basically, the center is defined to be the collection of all elements which gives 0 when bracketing with all the elements of Y. Okay. And derived algebra of a Lie algebra, we have seen this, the definition, but anyway, we can consider this commutator of G and G, which is again repeating span of XY when XY in G. So this is the derived algebra. So clearly, if G is abelian, so basically G is abelian if and only GG is 0. Fine. So now we want to call it G1, this notation. Then we can inductively define Gn. Okay, so G2 is G1. Okay, and then Gn can be defined to be Gn minus 1, Gn minus 1. So then G is called a solvable Lie algebra if for some n this Gn becomes the trivial space, okay, the trivial Lie algebra. So at once you get from here that if a Lie algebra is simple Lie algebra, then it cannot be solvable, because for solvable you must have an ideal. So for example, this G1, which is GG, is an ideal of G, and GG cannot be equal to G, because at some point it has to be 0 to be solvable. Okay. So clearly any simple Lie algebra cannot be solvable too. Well, nilpotent Lie algebras, in a similar fashion, actually, we define G0 to be 0 and G1 to be GG, which is again this G around bracket 1. But now Gn, we are defining this to be Gn minus 1 G. Then G is called nilpotent if some power n of G gives 0. So it's clear that any nilpotent is also solvable. Okay. So now homomorphisms. If we have two Lie algebras, Fi, a linear map in between them, is called a Lie algebra homomorphism if this happens. So basically, phi of bracket xy is the bracket of phi x, phi y. Okay. So we have seen that GLV, this is GLV. So we have seen that GLV is a Lie algebra. Okay, this side is a Lie algebra. This is the Lie algebra of linear maps. Bracket is commutator using the composition. So if you have any homomorphism from any Lie algebra G to such Lie algebra, such particular Lie algebra GLV, then we call rho a representation of G over V, or simply rho is a representation. So a representation is a particular homomorphism between two Lie algebras. And the dimension of this representation is defined to be the dimension of the vector space V, which is used here inside GLV. Now modules over Lie algebras. So representation modules, they are same thing, which will follow from here. So anyway, we want to define them. So suppose G is a Lie algebra and V is a vector space. Then we define an action of G on V by this. So basically, this is a bilinear map from G cross V to V. And XV goes to X dot V. So this is the action, how G acts on V. It must satisfy, so basically this is a bilinear map, first of all, and then it must satisfy this condition. So basically this condition says how bracket of two elements actually act. So bracket of two elements must act like this for V to become a module over G. Well, so module representation are actually equivalent. Why? Because if we take a representation rho, which is again G to GLV, a homomorphism, this is a homomorphism, Lie algebra homomorphism. So from here, you can actually write the module. So how G acts on V. So basically, from this information, we can write XV and X goes to this X dot V, which is given by, is defined to be actually rho X. Rho X is a linear map from here of V, and then it acts on. So basically, V is the argument of this function rho X. So this gives the action. Now, if a module is given, from there also we can write the representation rho. So if this module is given, then how to write the corresponding representation rho? So basically, if you want to describe rho, you have to define rho X, which is a linear operator, and what happens when it acts on V, right? So rho X V, simply you can define this to be action of X on V, and it will be a homomorphism from G to GLV, and therefore a representation. So basically, modules and representation are the same things. Okay, so for any Lie algebra now, if you ask what are the modules, okay. So one obvious module is G itself. So if G is any Lie algebra, G becomes a module over itself. How? What is the action? So xy must go to X dot V, right? So here V is Y. So basically all the elements are from G. So here the action is actually X dot Y, which is nothing but this bracket. Okay, xy. So then one can check that this is a valid action of G on V, therefore G on G. So G becomes a module over G. This is called this is a particular name for the adjoint module. So if you want to write the representation map corresponding to, basically representation corresponding to this module structure, then we can write in a similar way. So basically we have seen it in the last lecture, in the last slide. So rho xy can be defined to be just bracket of xy, which is we are introducing this add map. Okay, so this is defined to be add x of y. So basically, rho as a map takes what? Takes x to add x. So add x. Okay. So then this map gives the representation map, which is equivalent to this module structure. Okay. So ADX is called basically adjoint map, and this representation given by add, so given by this rho x equal to ADX is called the adjoint representation. So basically adjoint module here in case of module, and in case of representation it's adjoint representation. So any other module? Yes, for any Lie algebra G, if it has any ideals, okay, then all the ideals are also modules over G for obvious reasons. Okay, so some module, if we have a Lie algebra G and V a module, okay, and W is a subspace of V, then we can define this G. So not always, but if we can define, so basically if we can restrict the action of G to W, then W is a some module. Okay, so basically this is the same action as the original one. Okay. So suppose we define this x w goes to x dot w. X dot w is again inside w. W becomes a sum module. That's so basically it is possible to restrict the G action to w from V. Well, so obvious sum modules for any V, for any module V, the obvious sum modules are the trivial and V itself. Okay? They are obviously sum modules. Now irreducible modules, V is called irreducible if the only sum modules are 0 and V. Okay, so there is no intermediate sum modules between 0 and V. And given two modules, if we have two modules V and W, so we can actually give this direct sum of this vector space a module structure where the action is given by this x dot V is just act coordinate wise x dot V and x dot W. So this becomes a module then over G. This is called the direct sum of the modules. G modules V and W. Now, completely reducible modules. When V is called completely reducible. So if V is such that V can be written as a direct sum of irreducible sum modules, then V is called completely irreducible. And in indecomposable modules, if V is V cannot be written as direct sum of two sum modules, then V is called indecomposable. So it's clear that if some module is irreducible, then it cannot have some modules, and therefore there is no question of having the option of writing this V as a direct sum of two sum modules, right? If it has no sum module. So if it is irreducible, there is no sum module, and that must be indecomposable. But this is the other way is not true. Okay, so there may be some indecomposable modules which are not irreducible. So now we are in the main part of this theory. So basically, semi-simple Lie algebras. So suppose G is a Lie algebra, we can have ideals like Ij of G, and then if they are solvable ideals, which means Ij in themselves they are solvable Lie algebras, then I plus j can also be seen to be solvable. Okay, this can prove. And from there, one can prove simple dimension argument. One can prove that G has a unique maximal ideal. Okay. So if G is a Lie algebra, it has a unique maximal solvable ideal, which is called the radical of G. Okay. So now the definition of semi-simple Lie algebras, if for some Lie algebra G, the radical is trivial, then the Lie algebra is called semi-simple. Okay. So clearly, if a Lie algebra is simple, then it has to be semi-simple because it has no ideal since it is simple, and then no question of having solvable ideals or maximal solvable ideal. Now, since rad G is the maximal solvable ideal, if we quotient it out from G, then G mod red G ideally would not have any solvable ideal because this was the maximal solvable ideal inside G. So then this has no solvable ideal, which means no, so maximal solvable ideal is trivial. Therefore, G red G is automatically simple for any G. Also, once we know that which are semi-simple Lie algebra, which are solvable Lie algebra, there is this big theorem. Again, you will not see the proofs here. So characteristic, if you characteristic zero fields, if you consider any finite dimensional Lie algebra G, then G is just semi-direct product of two Lie algebras. One of them, so this is solvable, and this is semi-simple. So basically, more or less, any Lie algebra is made of a semi-simple Lie algebra, this one, and one solvable Lie algebra here. Okay, and then this solvable Lie algebra can be taken to be just the radical of G. Okay, and this factor is called Levy factor, which is semi-simple Lie algebra. Okay, there can be more than one semi-simple, basically more than one Levy factor inside G. There is no problem. And now, so if we know semi-simple Lie algebras and solvable Lie algebras well, to some extent, we know G, the Lie algebra G. So G was any Lie algebra. So one would like to classify solvable and semi-simple, right? But the classification of solvable is actually hopeless. Okay. Even for nilpotent, the classification is impossible. But there is a good news for semi-simple Lie algebras. Okay. The semi-simple Lie algebras, at least over the algebraic closed field of characteristic zero, they have elegant classification theory. Okay, well established, of course. And over non-algebraic closed field, for example, R, people also know the classification, but which is, I mean, as difficult as the complex case, the algebraically closed field of characteristic zero case, actually. So we can also sometimes talk that, okay, the Lie algebras are over C. So therefore, we do not try to classify solvable or nilpotent. We focus on classifying the semi-simple. So basically here, first we will move towards that classification of semi-simple. Okay, so for semi-simple, there is inherent bilinear form. So basically, if you have a Lie algebra, semi-simple Lie algebra of a field F, then if you define K to be xy, K of xy to be trace of adx composition ady, so the composition of linear maps, adx ady we have seen. So then this K is of course symmetric because trace of AB is trace of BA, and this is of course bilinear. This is another property called associativity. I have not written here. Associativity. Okay, it's a different kind of associativity, but anyway. So for any semisimple, we have this symmetric bilinear form. Sorry, for any Lie algebra, we can write this, the symmetric bilinear form. Now, this symmetric bilinear form is called non-degenerate if this hold. So the collection of all elements which are in some sense orthogonal with respect to beta to all of G must be trivial. Okay. So this is also called radical, but radical of the form beta. And this we can do for any Lie algebra G. Now, if G is semi-simple, then the scaling form is non-degenerate. Okay, and this is vice versa. So basically, this is an if and only condition for checking whether a Lie algebra is semi-simple. So if Lie algebra is semi-simple, then the killing form is non-degenerate. Okay, so this result is extremely useful, but we don't know how much of this we can use. So there is the important theorem. So suppose G is a semi-simple Lie algebra. Then there are ideals of this semi-simple Lie algebra such that G can be written in this form, and each individual ideal, they are simple Lie algebras in themselves. So basically, any semi-simple Lie algebra is a product of simple Lie algebras, in particular, simple ideals of G. And for semi-simple Lie algebras, there is this theorem. With that proof, we will look at it. So it says if you take any G, which is semi-simple, and any module, finite dimensional module over G, then this V can be written as a direct sum of modules. So direct sum of irreducible modules. So this is called the complete reducibility of modules, of finite dimensional modules over semi-simple Lie algebra. So this means if we just understand for a semi-simple Lie algebra, only the irreducible modules, then we know all the finite dimensional modules. Okay, so this is extremely important theorem, but we will not see the theory, the representation theory related to this. So in some coming lectures, we will definitely see them, because I think Professor Tanusri, I think, will be doing this. So now if G is a semi-simple Lie algebra, then there is an important fact to note that there exists element X inside the semi-simple Lie algebra such that add X, which is the linear map from G to G, is actually diagonalizable, or we call it semi-simple. Okay, so there always exist such elements. So one has to prove this, a long proof in several steps. Anyway, so such elements are called semi-simple elements of G. So basically, if add X is semi-simple, we call this element X to be a semi-simple element of G. So now if I want to consider the subalgebra of G consist of only semi-simple elements, we can do that, because there exists at least one element such that add X is, so basically there is at least one element X which is semi-simple, and then if we just take the span of this is itself a subalgebra, and therefore we have at least one subalgebra consisting of only semi-simple elements. Okay, now once there are semi-simple subalgebras consist of semi-simple elements, we can take them. We can take the maximal such. So basically, all these are called toral subalgebra. We can consider the maximal toral subalgebra, which is the maximal subalgebra, a maximal subalgebra consisting of only semi-simple elements of G. Okay. So those algebras will be called Cartan subalgebra. We will not say maximal toral again and again. We'll call Cartan subalgebra. So now suppose G is semi-simple, we fix one Cartan subalgebra H of G. And since the maximal toral we have seen here, a maximal toral subalgebra is abelian here. So since this is abelian, so since H is abelian and consists of only semi-simple elements, by our linear algebra result, we know that all these maps add H. So basically they commute. So all elements of add H. So basically add H is what? Add H is just add H belong to H. H belong to H. So all these add H, they commute with each other because add H, because H is abelian. So These are commuting linear operators, each of which is diagonalizable. Therefore, they are simultaneously diagonal. Sorry, ADH is written already here. So they are simultaneously diagonalizable. And therefore, G can be written as direct sum of G alphas, where alpha is in H star. Okay. So what is G alpha then? G alpha becomes the collection of all elements in G such that Hx equal to alpha Hx. Okay. So for some alpha, G alpha can be 0, fine. And this actually is a finite direct sum because G is finite dimensional anyway. So there are most of G alphas are actually 0. And what is G0 especially? If we check from here, so G0 is explained to G such that Hx equal to 0h. So that is 0, that's 0 linear map. So basically 0x, which is 0. So G0 is the collection of all x's which commute with all elements of G, all elements of H. Okay. So since H is abelian, this contains H. Okay. One important result here is that G0 is in particular containing H. G0 is actually equal to H. Okay. And therefore, we want to rewrite this decomposition. Okay. So G0 is H, and for alpha not equal to 0, if G alpha not equal to 0, alpha is called a root of G. So if G alpha not equal to 0, alpha is called a root of G. And if we collect a set of all roots, we name the set to be phi. So then phi is a collection of roots of maps in the dual of H such that G alpha is not equal to 0. Then phi is a finite set because G is of finite dimension. Okay. So elements of phi are called roots. So basically alpha is a root if G alpha is. So if the common eigenspace is non-trivial. So now we are rewriting this decomposition. So G0 was H, and in phi, inside phi, we are taking alpha to be non-zero. So there is no 0 here. And it becomes a direct sum of this form, like H direct sum G alpha belong to phi. This decomposition, I mean, very satisfying decomposition, is called the root decomposition, root space decomposition, or the Cartan decomposition. We will just say Cartan decomposition when we are referring to this. And Cartan decomposition with respect to actually H. If we take another Cartan subalgebra or another maximal torus, there can be many, another maximal torus subalgebra, then the Cartan decomposition is different, but it is again of this form. So H and then G alpha belonging to phi. And this dimension of H is an abelian subalgebra. Dimension of H is called the rank of the semisimple Lie algebra G. Well, so we have this decomposition. It's called the Cartan decomposition. Some observations are made here. So this is very satisfying because of this properties actually. So if G alpha, G beta, if you take the commutator, then it is inside G alpha beta. Okay. And this is the killing form. So if you consider the killing form of G alpha, G beta, then this will give 0. So basically they are orthogonal if alpha not equal to beta. Alpha not equal to minus beta. And this form can also be restricted to H. And this restriction of the killing form to H is also non-degenerate. Okay, these are all important to develop theory, but I am not going into the intricacies into my details here. Okay, so then phi, there are elements. So basically phi spans H star. Okay, and 0 doesn't belong to phi. We have seen this. And phi, so basically phi contains a basis of H star, and dimension of, sorry, this will be G alpha because the Lie algebras are G here. So dimension of G alpha is always 1 for actually alpha not equal to 0. Okay. And if alpha is in the collection phi, then minus alpha is again inside phi. And it is true that these alpha and minus alpha are the only elements inside phi who are of the form C alpha. So basically, if C alpha is in phi, then C is either 1, which is this case, or minus 1. Okay. And then G alphas, all these G alpha generate the full semi-simple Lie algebra G. So when you take all the brackets and possible sums. Okay. So clearly we have mentioned that phi spans H star. So we can choose a basis of H star consisting of roots, right? So call them alpha 1 till alpha L. Okay. So now if beta is in phi, if beta is in phi, so basically beta is a root, then beta can be written uniquely as this linear combination. So basically these are scalars, and these are the roots here. Okay, so any beta can be written as I equal to 112 Ci alpha I, where Ci are some scalars, but one can actually take, one can actually write this taking Ci's to be inside the prime subfield. So basically Ci belongs to Q. So once we can do this, then if we consider the Q subspace, which is called EQ of H star, which is spanned by all the roots, so all the roots alpha 1 till alpha L, then we get a Q vector space, which is called EQ here. Okay. Then the dimension of EQ over Q is, of course, L, which is the dimension of H star over the original field F. Okay. Why? Because we are just considering Q linear combinations of these. Okay. So Q span of alpha until alpha n. So once we have this real vector space of dimension L, we can extend the scalars by tensoring with R. So basically then E becomes this, which is a real vector space now, which is a real vector space now. Okay, and we have the killing form here, which was non-degenerate on the Lie algebra G. So that killing form, when restricted to H, we have mentioned that becomes that remains non-degenerate, and then this non-degenerate form on H can be transferred to H star, which again can be transferred to EQ because we have the basis of H star in EQ. And from EQ, we can transfer the same bilinear form to EQ tensor R, which is E. Okay. So, and this on E becomes positive definite. So basically we have, so basically E becomes a Euclidean space. Why? Because we have Euclidean space, real Euclidean space actually. So E is having one, so basically E is a vector space over R. So E is a vector space over R, and this gives a positive definite form, bilinear form on this. It is also symmetric. So E becomes a Euclidean space, and phi contains a basis of E, this we know, and dimension of E as a vector space over the reals is also dimension of H star by this construction. So summary. So in summary, you can state this. So we started with a semi-simple Lie algebra and a choice of Cartan subalgebra, right? This is the Cartan subalgebra, this is semi-simple Lie algebra. And we arrived at a Euclidean space with a collection of roots in that. Okay. What are the properties? So phi spanned E, and 0 does not belong to phi. And if alpha belongs to phi, then minus alpha also belongs to phi. Okay. And these are the only scalar multiples of phi which are in phi. Scalar multiples of alpha which are in phi. And these two conditions can also be proved. So if we take any two roots alpha beta in phi, then beta minus this thing is also in phi. And if you take any alpha beta in phi, then 2 beta alpha over alpha alpha, this term is actually an integer. Okay. So in Lie algebra theory, such collection, so basically such system is called a root system. Okay, so collection of roots is called a root system. In general, root systems can be introduced starting with a Euclidean space. So suppose E is Euclidean, so basically it is a finite dimensional vector space over R we are considering, and then it has a symmetric positive definite bilinear form. So this is it. This is symmetric and this is positive definite. Now we can take any alpha which is non-zero vector inside E. Okay, And correspond to this alpha, which is a non-zero vector inside this Euclidean space, one can consider this map defined by, so this map sigma alpha defined by this sigma alpha of beta given by beta minus 2 beta alpha over alpha alpha and then alpha. Okay. So then sigma alpha is actually a linear map, one can check, and sigma alpha is in particular a reflection map. So basically this fixes one hyperplane given by this. So this is the hyperplane P alpha, which is given by this. So all betas which are perpendicular to alpha. Okay. So this is a hyperplane, and one can easily check that sigma alpha fixes all of this, all of the elements of P alpha, and it takes alpha to minus alpha. So basically taking alpha to completely opposite of it. We want to abbreviate this. So basically this term 2 beta alpha over alpha alpha is used again and again. So we want to abbreviate 2 beta alpha over alpha alpha to be just angle bracket beta alpha. So now root system. So basically if we have a subset of E, okay, so finite subset, okay, so here it is added. So phi is called a root system if phi spans E. So the vectors inside phi, they span E, and phi is a finite set and 0 does not belong to phi. The second condition is if alpha belongs to phi and C alpha belongs to phi, then C is only plus minus 1. These are the only possibilities. If now we have alpha which is inside phi, then sigma alpha of phi must be equal to phi. So basically for any given alpha in phi, we have this map sigma alpha. Okay, now sigma alpha, so sigma alpha becomes a map from E to E. So sigma alpha is a map from E to E. Okay, so and phi is a subset of E. It just says that sigma alpha of this set is again the same set. So this is invariant under sigma alpha. And for any alpha beta belongs to phi, this quantity 2 beta alpha over alpha alpha, which was abbreviated to be beta alpha angle bracket, this must be an integer. Okay, so if all of these satisfy, then the subset phi is called a root system. Okay, so there is this notion of Weyl group connected to a, so basically related to a root system. So if we have root system phi, for all alphas inside phi, we can consider these maps sigma alphas. We know that they are just reflections in the Euclidean space. Okay, then we can generate a subgroup of this, and each sigma alpha, since these are reflections, so these are invertible operators. So basically each sigma alpha is an invertible operator. So therefore, if we consider the subgroup generated by all these reflections, then that is anyway a subgroup of GLE, the group of invertible maps on E. So we denote it by W, and this is actually called the Weyl group. Well, so whether it is finite, the answer is given by this. So W, so any sigma alpha, because of this, any sigma alpha just permutes the elements of phi. Okay, so the group generated by this cannot go outside this symmetric group on the roots inside phi. Okay, so if order of phi, so cardinality of phi is this mod phi, then W must be inside as this, and it has to be a subgroup. So in particular, W becomes a finite group, and this is called the Weyl group of phi. We'll not see a use of Weyl group now, anyway, but this is extremely important. And isomorphism root systems. So basically, we have these root systems we want to talk about when they are necessarily the same root systems. So suppose we have two root systems, E and phi. One root system E phi and another root system E dash phi dash. So they are called isomorphic if there exists a linear map, of course, linear isomorphism E to E, which takes phi to phi dash. Okay, so basically this is an onto map. So this is mistake. So psi is a linear isomorphism from E to E dash, which takes phi to phi dash. Okay. If this condition holds, then this is called an isomorphism between root systems. So basically, psi beta, psi alpha must be equal to angular bracket of beta and alpha. So then we call phi and phi dash to be isomorphic root systems. And for root system, there is also something called rank of the root system, which is nothing but the dimension of E. Okay, so what is root system? So if we consider rank to be 1, then the dimension of the Euclidean space itself is 1, right? So this is just a real line. Okay, so if rank phi is 1, which means dimension of E is also 1. So this is just a real line, and we can actually draw the root system. We can give a picture of the root system. So basically, suppose this is alpha on root, then minus alpha must be there here, and now no other can be here. Okay, because these are the only. So if anything else has to be here in the root system, that has to be a constant multiple of alpha, because we are in the one dimension case, and we know that the only constant multiples are just alpha and minus alpha. So basically 1 and minus 1. So this is the picture of rank 1. This is the only possibility, rank 1 root system. If rank 2, we can actually draw all these, and one can check that for all of these, all the requirement for this to be root system we'll go through, and it turns out that these are the only. Okay, this theory will not do today, but okay, classification root system we'll go over them, but not today. So it turns out that these are the only root system when rank of phi is 2. If rank phi is 3, then it will be so basically here dimension of E is 2. If rank of phi is 3, then dimension of E must be, I mean, obviously it will be 3, and we cannot draw nice pictures, but okay, these are all the root systems in 2 dimension rank 2 case. So for any given root system, there are some special roots inside phi, so which are called simple root. So basically, if this is a basis of, so basically this is a subset of phi, which is also a basis of the Euclidean space, and any other root beta inside this, basically any root of the root system phi, if they can be written uniquely as this integral sum with all k alphas, either non-positive or non-negative. So basically, any root inside phi can be written uniquely as summation k alpha alpha, where alphas are coming from this subset. Okay, and this subset must be a basis of this. Then the roots here inside this triangle, okay, inside this set, are called simple roots. Okay, and obviously, then cardinality of this set is actually dimension of E, which is again a rank of phi. Okay. So what are irreducible root systems? So if phi is a root system, and if phi cannot be written as phi equal to phi 1 union phi 2, such that phi 1, this is the bilinear product, which is available on bilinear form, which is available on E. With respect to this, if they are orthogonal, then phi is if phi cannot be written as phi 1 infinity phi 2 with this property, then phi is called irreducible. So in this case, phi is called irreducible. So basically, for example, if we come over here, so this is alpha, so this is minus alpha, right? So this is alpha, this is minus alpha. Okay, so if I write alpha minus alpha on one side, and this is beta, and this is minus beta, right? This is, of course, minus beta. So beta and then minus beta. So call this phi 1 and this phi 2. Then clearly phi 1 is orthogonal to, any element from phi 1 is orthogonal to any element of phi 2. Yeah. So phi 1, phi 2 is actually 0. And therefore, this is not irreducible. This is reducible. So why we are introducing this concept of irreducible root system is that so we want to study only the irreducible root systems and then any other just union of them. And in picture, any root system is just a so basically this is it can be said as union of these two terms. So basically alpha minus alpha and beta minus beta. So basically after notation, this is again alpha minus alpha. Right? So but this is irreducible. These all are irreducible. This is the only reducible case here. So irreducible root systems will correspond to irreducible semisimple Lie algebras. Therefore, we are doing it. Sorry, irreducible root systems will correspond to simple Lie algebras. Okay. So basically, we are moving towards classifying the semisimple Lie algebras. Anyway, so Cartan matrix. Suppose we have this base of a root system. So some roots are there. We want to write them in a particular order. So this is written in order, alpha 1 to alpha L. Okay. So these are all simple roots. So basically, these are elements of the base. Out of this, we can actually construct a matrix where the entries are Aij given by this angle bracket alpha I, alpha j. So this becomes an L cross L matrix because there are L elements in the basis. This matrix is called actually Cartan matrix. Okay. So why Cartan matrix is important is because of this proposition. So basically, Cartan matrix of a root system actually determines phi, the root system, up to isomorphism. Okay. So if you see that two Cartan matrices are same, so basically this corresponding entries are same, then corresponding alpha I, alpha j, and another Cartan matrix, let's say given by beta I, beta j, if they are same, they are coming from necessarily the same root system. So basically, their root systems are isomorphic root system. Some properties to note on here is that Aii always 2. Aij, basically all the entries must be of this form, which are non-diagonal, I not equal to j. If Aij is 0 for some ij, then Aji must be 0. And if Aij is minus 2 or minus 3, then Aji Aji must be minus 1, but not the other way. So basically what we have done, so we started with one semisimple Lie algebra. So we started with one semisimple Lie algebra, okay, and we fixed one Cartan subalgebra. Okay. From there, we could get one Euclidean space E, and then a system of roots inside E. So this is, of course, as a root system. And from there, we could find a base of the root system. So base of the root system, and using that, we have written a matrix. Okay, let me write just a matrix. So it's a Cartan matrix. The Cartan. So we understand matrices better, right? So from semisimple, we have arrived at a matrix. So from matrix, we will arrive at some diagram called infinite diagram. Okay. And then we'll mention the classification result, okay, in terms of maybe these diagrams or even in terms of Cartan matrix. So basically, we are moving towards classifying the semisimple or simple Lie algebras. So if phi is reduced, so basically phi is irreducible, then we are classifying the simple Lie algebras actually here. So I'll stop here and let me know if you have any questions.
So have you given the proof of this statement? This Aij is equal to 1.
No. Proofs are out of scope.
You will not give.
No.
You will slip.
So it's really very difficult to give proofs of anything written here, unless it is very trivial.
So any question?
This will take
Well,
at least one lecture, one hour lecture.
if there is no more question, okay, any question? I'm asked. If there is no more question, let us unmute and thank the speaker for a nice talk. And
Thank Munna also for sharing this, and let us
okay, so
Samir
let us
meet
close the
tomorrow,
session.
the day after tomorrow.
Okay.
Ron,
Okay,
can you
so
stop the recording and live stream?